Hey everybody, I hope you can hear me now. Hi Philip, welcome to the chat. Nice that you tuned in, and welcome to the next potato stream, starting as always as a potato with some issues. So, microphone issues solved, camera issues solved. In case you are wondering what we're doing today, I can also remind you to look into my YouTube. Here's the link. All previous content, the interesting previous content gets uploaded here. And today's content surely will be found there sooner or later. Today, we are focusing on my home soil, so to say. We are focusing on post-processing. Maybe you're following me on other platforms like LinkedIn. Then you know that my profession is computational fluid dynamics. Yes, of course, but especially making them look wonderful. And that's what we are talking about today. First of all, I want to give a formal introduction what makes a simulation visually compelling. And then we are going right into some simulation that I have prepared for today. Some of you might know it. It's the so-called DrivAer. It's an aerodynamics model by TU Munich, but I will give a formal introduction on that model later. So first of all, let's take a look what makes simulations so compelling. Maybe some of you know this simulation here. That's the fluid film wiper. It's just an animation of a simulation that goes left, right, and swipes away water from a windshield. It's a volume of fluid simulation. So we are having two fluids present. And yeah, of course, it's multiphase then. And it uses some new split up droplet models that are quite new. The thing is, what makes this so visually compelling is that it's totally relatable. You see that picture, there's no explanation needed. You instantly get what this all is about. So it's no effort at all. So it's just black geometry, then an environmental map. This one is actually standard and comes built into SimCenter star-ccm Plus, as I can later show. And then there's just an ISO surface, a preset material as it seems to be. I'm not sure if it's glass sheet or glass body. And then somebody should adapt the refraction, the index of refraction, if necessary. To be honest, when I looked at this first, I thought, yeah, that's the standard 1.51 index of refraction, which is typical for glass, not for water in this case. Yeah, water would be more like 1.333, and it might even give a more natural impression then. So that's how you make a CFD simulation look wonderful. Next one. This is the one we are talking about today. So why is it compelling? Maybe you have seen it yesterday on my LinkedIn post. It's a I got very nice feedback for this one. Despite lacking geometrical fidelity. That's an issue with that DrivAer. It's just a car, just the outside body. There are some engine compartments and different parts there, but there's nothing like the lights. There are no separate patches for the headlights. Even the Sim Center logo here in front is fake, so I added another geometry for that, just for visual display. And the inlets are just all closed, and I split some geometries there. That's hard because it's not geometrically interesting. But what makes it interesting is the large eddy simulation. This just has high fidelity flow structures. You can see so many tiny swirls here and there, and that makes it visually impressive. What is the displayer that we are seeing here? Well, it's just Q criterion isosurface colored in velocity magnitude, partly transparent color map. I will show later how you make these partly transparent color maps. Of course, I'm a Siemens employee and this is our simulation, so I took the Siemens color scheme for the color map and all geometries actually. Since the full picture is filled just with rendered geometry, nothing like a background, which doesn't need to be re-rendered, it has some interesting long render times. But that's just the issue for the workstation, not for us, right? Okay. Referring back to Siemens colors, if you're working for a company and you want, or a university, and you want your visualization to speak, yes, it's from that company, then take your color scheme and make a CFD color palette out of that. So, for example, look at this one here. We have that red, we have orange, yellow, bright green, dark turquoise, going into blue and dark blue. So look at this. Here we go. This one, maybe this one, going here, and then bright green. Yeah. Siemens petrol, going to blue, maybe skipping that one, directly going there, and deep blue. That's it. Okay. But what did I mean by saying all the geometries? Well, actually, look at the body. Look at the glass wall on the side, here, background, and the nozzle. That is other colors from here. So we have this light gray, soft gray, deep gray, the sand colors right here, yeah, that go into the surroundings. And the whole image speaks Siemens from my perspective. And I love it. That's corporate branding in CFD. Try it out. If you want to get a small hint how to create these wonderful color maps, in a blink of an eye, I have an Excel document prepared and some Java macros. Just reach out to me. I can share it. That's not a big deal. Yeah. Okay. Yes. And that's how you get it visually impressive. Next one. So, next color map, that's also 100% Siemens. We have yellow, orange. Yeah, they call it red, going into purple, dark purple, and I guess it's going into dark blue, maybe even black. And here we go. But this one has some flaws. You should pay attention to it. Here at the back, we have the tires even colored with the flames, right? It's just because they are overlapping displays, and I made some tricks to show the geometry like that, because I just zoomed out by 0.1% to make this look interesting, and you can see that they are not at the exact right place here. Yeah. I couldn't do anything against that at that point, but if you bear that in mind, you can counteract it before you start the simulation. So in the simulation, all this was just one boundary. Yeah? So you can either show or not show the whole boundary. I'm not saying increase your boundary count until infinity. No, don't do that. But if you had just splitted the windows and the main bodywork from the rest, that job would be so much easier. Because then you can say, okay, I'm showing the bodywork, or I'm showing the windows, I'm showing something else here and there. Yeah? That gives you a lot of opportunities. Okay. Horrible render times as before. Yeah. And there's another issue you can see here. It seems to be a bit noisy. Yeah, there is some noise. And you can either opt for having less noise, but this will delete the light effects here on the windshield, or you make it more noisy and have these brilliant effects. So it's up to you. It's a choice of your preference. I personally prefer to have it a bit more noisy, but more brilliance in it, but it's as you like it. So, okay, that's not the Eclipse, but that doesn't matter. Next one, the mixer, same here, no geometric fidelity, basically, yeah. But we have multiphase flow. We have a dense liquid here in black poured into another less dense liquid and free air above. So we have three phases, right? And what we are doing is we are showing the fraction of mass of the dense fluid. So it pours into here and gets mixed, and there's there are some interesting flow structures then evolving. It's all mixing. I guess I have worked on that one in another stream, so I'm not focusing on that one here. Yeah. Oh, I might have to upload this one, the previous stream still. Okay, next one. And that's like one of the first big hits I was involved in. That's a rotor blade Aeroelasticity. And it has a ton of geometry. Yeah. Even though we are only simulating like the outside of the helicopter, we have the full helicopter here, and we see everything. We see the different body parts, the tires, the nose, and whatsoever. And this visually speaks, yes, it's a high fidelity, it must be precise. Might be misleading, but you never waste a high effort on bad simulations. So here it's not especially interesting flow structures at first, but it's interesting geometry that makes the image compelling. We have a very nice suiting background, yeah, and we have some interesting feature as well, which is the two-way coupling between the stiffness of the rotor blade and the movement of the rotor blade with the flow field around, which is still unsteady Reynolds average Navier-Stokes, but can be interesting and insightful as well. Yes. One thing I want to particularly highlight is that motion blur in a static image. And that's just for static images. We have duplicated the displayers for the rotor and then set it to, rotate by +5 and -5 degrees. So you get this blurry impression in a static image. And that's sometimes quite hard to have a static image that says, yeah, this is a dynamic scene. Yeah, there's really going on a lot in that scene. And this is why, this is how you can get some dynamics into a static image. What's shown as a displayer here? Yeah, it's vorticity magnitude isosurface displayer. And it's just glass sheet preset. You could increase or decrease the index of refraction here and play a bit around to make it look more or less realistic. The thing is, for clear air, the IOR is nearly 1.0000000 and then there's a digit or something, but that's not really visible. So you increase it a bit and then you get that blurry contour around that isosurface. Right. Yeah. What's next? Okay. The eclipse. One of my personal highlights, so to say. Because we have combined extreme geometric fidelity and extreme flow field fidelity, which in this case is wall-modeled large eddy simulation. Again, we have the Siemens colors, red, yellow, orange, taken from the Siemens color map. But in this case, we have taken the other colors, like the dark blue, from the surrounding background, from the background. So the dark blue is picked somewhere here, and the light blue is picked somewhere here, and so that it matches the image. How do you get this? Picking colors. Picking colors is so easy. You just get your Power Toys by Microsoft on your Windows computer, and then you can have a color picker in there. I will show that in English next week, supposedly, because I need to change my OS language into English to record it properly. Yes, then you can pick colors from the background and include it into your color bar. What quantities do we see here? Well, at the top, it's off-body vorticity around X. So you have the flight direction and then the swirls in one direction and the other direction. So you can see on the right side of the plane here, it's more like reddish yellow, and on the other side, it's more bluish. Transparent, actually. And the bottom visualization is basically the same like the DrivAer. It's isosurface Q criterion colored in Mach number here. So we don't take velocity magnitude here, but Mach number, which I thought might be more suitable. There is a second isosurface for extreme high Q criteria, which is just present behind the turbine, and it's light emitting. Same color, same range, and that's why it gives that burning effect around the turbine. I thought it would be nice. But I have heard comments that, oh, your plane is going down. It's not. It's not. It's just turbulence. But yes, I like it. Yes. That's like the old ones. Another interesting visualization is my battery. And here we have an accumulator with some geometries, and I just added some random vehicle with full cut in the background to give the simulation some context. Yeah, just not showing it on a white background. Yeah, that always seems unrealistic. I have added a glowing effect to the battery, which I can show you later how it works. So it's basically one exactly where the geometry is. That's like the surface color. And then I add a light emitting displayer a bit away from that, which has opacity 0. And then the color bar is shifted a bit to brighter colors. Okay. If you want to do visualizations like I do, you should most likely set your advanced rendering settings to values like these. So 0.5 for quality, 0.2 to 0.7 on your noise reduction. That's up to you. But the most important thing is min-max samples per pixel. This is just how many times is a pixel re-rendered. And this is min-max. Yeah, it's easy. The quality is actually a logarithmic measure for the average sample. So if you turn that up, on average, the pixels get re-rendered higher times. Yeah? As needed. Yes. Furthermore, make sure for all displays to enable the shadows. Yeah, that's quite important. Yes. This is a short introduction to what we're doing today. So let's go right into the simulation itself. So imagine you have run your DrivAer simulation, and this is what it looks like. Yeah, or maybe even worse. You just made your first scalar field in here, and normally it looks like this. Yeah. Hi AAA 1029, nice to see you again too. Yeah, as always, you're at work. That's great. I will record the session. The session is recorded, and I will share it later on YouTube. You can find the content here. That's nice when I read the comment and it says I can't listen to the answer in the last sentence. Yeah, that's a bit too late. Sorry. Now I answered it for everybody. So this is where you start when you have that simulation run. Yeah. Please be aware that I'm only working on a Reynolds average Navier-Stokes simulation here. It's not a large eddy simulation. Thank you, AAA. Thank you. That means a lot to me. Yeah, it's not a large eddy simulation just because my machine cannot handle it at that point. Maybe there might be an update sooner or later. Who knows? Yeah. Okay. Typically we start at that. Yeah, just right here. We have some wall shear stress. Why do we look at wall shear stress? Well, you can tell where there is flow separation at any point. And what engineers might do is limiting the interesting points to something like, so typically engineers might just leave it like that. Yeah. Some go further and say, okay, I make changes like that. And that's it. And that's our starting point right here, right now. So what I'm doing is I'm copying this displayer and work myself from there. So first of all, we link the displayers, which means basically if you have them side by side and you rotate one, the other one rotates as well. Whoop whoop. Yep. So we are calling this beautiful view. Okay. Good, 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 good. Yeah. And yeah, that's where we start. Later we can compare it to the engineering view. So first of all, that's nonsense what we are seeing right here. Yeah, nobody needs to know what the wall shear stress magnitude is. 4.78 times E minus 22. That's just ridiculous. If you want to keep it at that value, you should go for 0 here. Yeah, come on. That's not even art what I'm doing right here. That's like common sense. Just rectifying your legend here. Okay? These are numbers humans can deal with. And we are not going for what was the original value here, the max value. Even that's kind of crap. Nobody needs to know the value like 18.411. Nobody can treat this. If you want it as max value, just go for 18. Enough. I'd say you most likely everything is here in that spectrum. So the 18, I don't care about that. So we're going down for just 3. And still, there is so much in the upper range that we're not interested in, but we are more interested in the lowest range. So what I'm doing here is I'm going for 0.03 to switch to logarithmic. Yeah? Because I want to see where we have flow separation. So here's a point. The whole back will be red, and there's a big zone on the rear window which is also red. And before we all get traumatized by the colors, we should change this as well. But first, let's increase these color levels. So we are going for 512 here. Not a big difference. Yeah, only the color bar has brought some changes. So this has to do something with the contour style, which is currently still set to automatic. We are going to set it to smooth blended. And you can see, yeah, that looks way smoother. But you cannot really distinguish from before. So let's revert the previous changes and just go for 32. And then you can see, yes, it makes smoothly blended fields of constant color here. Yeah? It's not like that's the actual value in the cell or on the boundary face. Yeah? If I want to see this, you could need to go for the contour style. Filled. That's the actual value. No, come on. Filled. That's the actual value. You can even see it when you turn on the mesh. See? Every single face has one value. That's the physically correct thing. That's what we simulated. That's our simulation result. If we switch to smooth blended, see what we do? We are interpolating around that and finding a line through all the cells to have one volume. That's not the numerically exact representation, but that's more realistic at that point. Because nature doesn't make any jumps. So we're not jumping from one cell to another with a different value. So we're not jumping from red to yellow here. Yeah, that doesn't happen in nature. Okay, so let's go back to 512 color levels or something above 200, which is just okay. Okay, turning off the mesh again. Still, that looks ugly as hell. What can we do? We can change the color bar. So you can see that I deal a lot with color bars. And that's actually the one from my university, my master's university. Yeah, I still love that really, really much. Yes, but today we are going for something different. So we take the Siemens Fire Advanced Rendering. This one right here. Pretty close already to the images we had in mind, right? I already like it. So there's still an issue. When you look at this here or at others, you get the impression, like here, that it's not evenly spread over the whole color bar. Yeah. This is something you can tune in your simulation, and that's called the ramp type. I personally prefer the linear ramp type because it's exactly like what you have set here. Okay? Good. And we are switching back to Siemens Fire Advanced Logarithmic. Bam, here we go. So here again, this is linear. This is the standard. What? Sorry, I misclicked today. This is the standard. And this would be S curve. You can already tell that it changes the color style. You can choose whatever you want at that point. Yeah, it's up to you. Furthermore, what I'm doing here is already something, I'm automatically doing some things that make the simulation easier to perceive. Yeah, I'm trying to highlight what we are looking for. Highlighting here, small areas like that. Small areas where the flow is separating. Yeah. But we hardly have areas where we have where we go into the wall shear stress magnitude of 3 or above. So one could say the upper limit is not correctly chosen. So maybe reduce it to 2. But now we get another issue. See, here we have some decent value. Here we have some decent value and some crappy value in between. Yeah, I don't like that. This is why I would always go and tune my lower values so that we have a ramp that is just nice. For example, go for 0.2 here. 0.02. Yeah, so we have our legend here. 0.02, 0.2, and 2. If I had something like, don't know, 0.002, the middle value is yeah, not nice again. Then I have like three orders of magnitude here, and I go for another number of labels. So I go for 4 labels. So I have 1 label for every order of magnitude. I think that's just better. Yeah, you can instantly see, okay, that's a logarithmic scale. Yeah, I'm going times 10 times 10 times 10. Yeah, and I can see, okay, white is here, very low, yellow is here, pink is here, and this is here. If you have something positive and negative, you should go different, but that we can do this later. So going back to 3 levels and going back to this here. Yeah, that's right. It might be that your color bar looks like this at first. And I would never go for this in that case. In that case, you are highlighting the areas where you have a lot of wall shear stress, not where you have separation, like here and here and here and here. Yeah. If you want to highlight separation, then don't go for a color scheme like that. Reverse it. So highlighted is what you're interested in. Okay? Cool. So let's make it look better. So to make it look better, we should add some context to it. And for that, we put a street below. So here we have the simulation and we have the floor. So we're putting a new displayer in here and yeah, calling it floor. If you ever get a simulation that I had my hands on, all the displayers will have numbers. So I sort like the geometry objects together in like the 90s range. I sort my velocity scalars in the tens range or something like that. Just keeping some order. But at that point, we're not dealing with hundreds of displayers, we're dealing with 10. So that's okay. Okay, let's make a floor out of it. Yeah, we don't see it. Why don't we see it? Because we have the representation latest surface volume. And we're switching that to geometry. Oh, you can instantly see that's a half model only. So let's switch to symmetry. Ta-da! Nice. Okay. Next step is make the projection mode perspective. Yeah, we already have that. Why do we do that? Yeah, let's compare it. Parallel. Parallel is nice for side view, for example. For top view, which is actually pressing S on the keyboard and T on the keyboard, and front and 2 times front is back. That's the F key, S key, and T key. That's not so important. But every other perspective and the car looks distorted. No, thank you. Perspective, way better. People might think that you can now just turn on advanced rendering and see some great effects. Yeah, well, no, we don't. Yeah, all we can hear is all our workstations spooling up. Be careful to click that button while you're streaming, because it might take all your computer resources. To limit your computer resources as well, or to set it correctly, better to say, go for tools and options and then to the visualization node. And when you make it bigger, you can customize several things. So you can set your default color map, which obviously is Siemens at my system, but could be your university or your company standard theme or something like that. And here you can enter the number of client render threads. This is how many threads of your computer will be used for rendering. Unlike simulating, the rendering uses hyper-threading or simultaneous multi-threading. So you can actually go for not only the physical number of cores that you have, but typically twice it. So if I looked at my computer, sorry, I just have an issue here. The window is just too big. Sorry. So if I looked at my computer here, it says, yeah, I can't show it, but it says 16 cores and it has 32 threads. Yeah. For simulating, I'm only going for these 16, but if I'm rendering, I'm going for 32. Okay. Couldn't make it any smaller. So see here, I have cores, 16 and logical processes, meaning threads, 32. So I could enter 32 here, but as I'm running some extra programs for streaming, I can't use them all, so better go for something like 26. Okay? Good. Then here we go. Clicking that holy button to see nothing change. Why doesn't anything change now? Apart from my CPU spooling up. Because we haven't set anything for the advanced rendering yet. Yeah? We have set wrong quality here. That's why it's taking so long at that stage. And first we need to correct that. So I said min 1, max 400. So it will start anew right now, and at least it's finished. I typically go for 0.5 in quality, which will cause it to restart, and it's directly gone. And 0.5 for noise reduction here. Yes, good. But still, that doesn't change anything. What's wrong? Nothing is wrong, actually. We don't have materials set that can be rendered properly. So we go for the advanced rendering. And so we go for our scalars here. So first, there's a new node, which is advanced rendering effects, and we can enable shadows right here. There's a small difference. Rendering starts anew. See? In the darker parts here we have a shadow, and in the wheel arch we have a shadow. Yeah, that's like the first difference. But the bigger difference comes when we switch the materials from non-physical at that point to a matte displayer. And now it really gets rendered anew and a different representation appears. Yeah, still no big changes at that point, but this will come. We can add a clear code here, which would be typical for a car body. So let's go for 1.5 index of refraction. That's like a very, very thin glass layer on top. So glass index of refraction is 1.51. So 1.5 is close enough. And here we go. We have reflections on the body. Bear in mind that you only can reflect what is there. Yeah, we have a boring white background. Yeah, that's all that can be reflected. Still, it looks more like a car right now. Okay. We could also go for metallic. This would look like this, and it gives a grayish image. That's interesting. Even it turning into green slightly. Okay, nice. We could also add an index of refraction clear coat layer here, which I call Christmas balls, typically, because it gets this metallic and shiny surface, which is a bit too much for me. We will reduce this again, and we can delete the roughness if we want to. Yeah, that looks a bit more like metal, but yeah. I don't think that's appropriate for a car body at that point. Maybe if we had a constant paint. Or maybe if we add some clear coat as well. Nah, not that really worth it. Right? Could work for the rims, but not for the car body. Okay, what else do we have? Yeah, we have transparent body. It does what it says. Yeah, but you can't really see the colors right now. I don't like it for this occasion. And we can go for transparent sheet. Might be a little bit better as a representation, but isn't working for me. Light emitting, yeah, we might use that one later. So let's go for matte displayer. And yeah, keep it like that. So next thing, the floor. The floor still looks like, what has it? It has a color mode constant. Yeah, we should change this. But first, we are adding a shadow here. Ta-da! The car stands on the ground and is lighted from somewhere and has a shadow. So, we could change the material right here, or we just say, I pick some presets. And as this is my job, I should have plenty of presets. I don't have the preset that I want here. Some of them are marked. That's interesting. Some of them are not. Okay. So, yeah, let's just take some dark gray for the floor, right? Yeah, almost looks like a street. Okay. Next thing, to make it look like an image, not like something the engineer looks at every day. Nobody needs that here. Okay? Put it away. And even though I'm very proud of my company, you will most likely never find me having the logo of my company in my work. It is somewhere around here. Maybe you can see that it says SimCenter star-ccm+. Yeah. I can put it into the foreground and then, well, yes, it's blue, so you can hardly see. Okay. We have put it, we can put it away. Just, it's gone. But if you want to, you can add your company logo anywhere. Right. So, yes. what else can we do? We can play around with lighting. If you look into the lights, there's one light enabled. Typically for advanced rendering, I turn this off. Doesn't make much of a difference? I think so. Because that's always static at the same position, lighting from somewhere here. Yeah. And no matter how I turn the car, it's always lighting from here. Okay? So, put that away. Nobody needs that. Okay. We're at that point already. But that's not fit for movies. We can switch the transparency mode, which sometimes helps us a bit. Yeah, I typically always use depth peeling, even though I'm not sure what it really does. Next thing is we are changing the aspect ratio, because there's nothing worse than exporting it and showing it somewhere and another animation, and they have different sizes. So make sure that you go 16:9, and every time you export it, yeah, just make it full HD or whatever you think is suitable. Yeah, for me full HD is the way to go, but in the future that might go up. Yeah, so 16:9. One could now argue that you could look for some golden spiral and make the proportions of that image perfect. I'd say that's not really necessary at that point. Okay, let's maybe just add some more fidelity to it so we have a nicely looking image. Next thing for me is the background color. So we can go for environment map. Well, what's that? And here's an environment map. Typically, yeah, let me zoom out. It looks like this. It's some surrounding from somewhere. There's some presets in here. Yeah, but it's tilted. Yeah, it just has a different coordinate system. So we go for -1, 0, 0, 90, turning it a bit around. And maybe restore a view that has proven to be nice. And now you can see how the reflections have changed on the car, right? The reflections are now from the background, not from a white sphere that's somewhere. We can also go for others, like the dirt road. Yeah. But make sure that it fits nicely into your surroundings. That's not maybe the best view, but should be nice for now. Okay. We got the background, we got the floor, we got the car. Let's highlight a bit more the bright spots. So this is the body. And now let's focus on the highlights. For that, we just copy this displayer and paste it again. Yeah, we don't see any changes because we just duplicated the displayer. So we say highlights here. And at highlights, we go for some differences in the advanced rendering. Instead of matte, we go for light emitting. Yeah, now it's like that. No, wonderful. Nobody needs that. Let's change it a bit. We will make this 1% bigger now. How do we make this? We are going for tools right here. And make a new transform. So for the new transform, we just say here, come on, simple transform. And this we will call zoom. As you can see, I already did this task before. And then we enter like dot 01, 1.01, 1.01, which is zoomed 1% in every direction. And then we also need a symmetry, as we will see later. So let's first change this transform. We click on the displayer and then we go down into our properties. And here we have transform. So we go for, I called it zoom, I guess. And you can see it's only on the left side, right? You can already tell it's 1% bigger now. But we need to mirror it. So what we are doing is we are putting a superposing transform here. So we say new graphics transform, and then we say symmetry transform, and it says repeat. And for plane, it takes 0010. No, that's not the right one. We're taking 0100, which is the Y plane. And we call it zoom symmetry. And we apply it to highlights. Zoom symmetry. You can also enter this mode here and then look deeply into all of them. See, that's literally just the same. Okay. Hey, super. Now we have a 1% bigger car and nothing has changed. Okay. If we now turn the opacity down to 0, we will just erase the surface representation of the surface and leave the lighting effects on. See? We can directly see that the render time is going up, but we have that glow around the wheels here and there, and the glow on the hot spots. Yeah, I think that's very nice. Turning it off again. Yeah, that's a difference, right? Yeah. Yeah. We can even tune this further by changing that color bar. Maybe you have noticed that we now have two color bars overlapping just right here. So first of all, we are not showing this. Now we are not showing the body color bar anymore in the background. Just say ciao, not visible. And we go for here for the color bar. And maybe we can also put that shadow away. Yeah, that's maybe better. Put it up here so we can see. And now we are customizing a copy of this to have more bright spots, I think. So what I'm doing here is I could customize the color here if I wanted to, but I'm only customizing the position, making this a little bit closer. Normally I'm just working with evenly split numbers or something. I don't like dragging them around and having it somewhere like this, but that's like personal preference. You can directly see what happens to the car when you work on that. Yeah. That's maybe even a bit too bright. I don't like it. I guess I'm turning back to the original, which was something like this. Well, that's decent. But maybe we can make it even better by increasing the light emitting intensity to 5. Ooh, that's over bright. Yeah, let's keep things real. Maybe 3. Yeah, that's decent. Because now even the violet areas have some lighting effects, right? Okay. Want to compare this to the engineering view? That was our engineering view. Small difference. And still, here you can see what in which spots the flow is separating. Here you can see even better in which spots the flow is separating. Yeah, one might argue, yeah, but this is not an exact representation. I would argue neither is that. This is misleading from a perspective standpoint, because we are not able to really see the green as intense as the yellow and the red. Plus there's my screen, plus there's the stream and whatsoever, right? Yeah, but if we want to have a perceptively correct representation, then we would go for something like that, which is even more ugly. And then people might say, yeah, but this is not barrier free. What if people cannot see colors correctly? Or correctly? Who sees colors correctly? We can't as humans, obviously. So, is that better? Isoluminant? I'm not sure. Shall we go for grayscale to make it easier for everybody? Yeah, I'm not sure. It should depend on your company. If your company says, yeah, we have people that cannot really perceive this or that color, you should change your CFD color bars. It might even give you a new perspective when you're looking at things. Yeah? Okay. But all I can say at that point is one color bar is as wrong as the other, and none of them is perfect. So why don't we use something that is compelling, visually compelling? Yeah? Because that's at least better than the standard one, but yeah, let's stick to this. Okay. So now we have wall shear stress. Let's make some positive and negative thing, because that's something especially to focus on. So I'm just hiding my 2 displayers and putting the advanced rendering in off. Hiding my background. So we're switching this back to solid white. And what else? Yeah, we're duplicating the body right here, right now. Oh, let's just start over. Doesn't make any sense. So we are going for our region here. Region, come on, region. Car body. Guys, I have split it already. We can do something interesting. So let's take the car body and make a scalar with it. Okay, here we go. That's just gray. So let's take the pressure coefficient, shall we? And we can see it's totally off. Why is the pressure coefficient off? Yeah, because nobody has tuned it correctly. So for that, we go to automation, field functions, and pressure coefficient, reference density. Let's see if we have a parameter here. No, we don't. So we need to guess that the reference density is 1.18415. And the inlet velocity, yeah, we can look that up. Inlet physics values, velocity magnitude, 20 meters per second it is. Interesting. Pressure coefficient. Where is it? Where are you? Here you are. So 20 meters per second. Yeah, looks better. Yeah. Why is it so ugly? Yeah, I can tell. Because we don't have light. For this, we need light again. We can really see something again. Okay? So, no, I didn't want to go for pressure. Did I want to go for pressure coefficient? Yes, I wanted to go for pressure coefficient. So this is, we call that child pressure coefficient. Pressure coefficient. And we should take the symmetry here. Okay. Yeah. First of all, we want to see positive and negative pressure on the body. So we are limiting the pressure coefficient to 1 at the upper end and -1 at the lower end. Looks like that. Okay. When you have positive, negative, please do so with your color bar as well. So what works for positive, negative is something like, yeah, this could work. Blue, yellow, red, color comfort, whatever. This could work, but I don't like it. I'd use something with white in the middle. This is a preset that is also great for showing the differences between square root, linear, and S-curve. Yeah, going for linear. Yes, why not? So let's just say we want to have cool warm, but for our company. So let's do it. Let's add a copy and say cool warm Siemens. So what's the color space here? It's not divergent, it's RGB. And then we need to make some changes. So first of all, we're putting white in the middle. Here we go. White goes to middle. And then we need a blue. RGB. And for the blue, we will take something out of the Siemens color scheme. Here we go. We take our power toys to look up the combination, which is Windows Shift C for colors. You can see, yeah, shall we take the dark blue or the light blue? Yeah, let's take these two, right? Picked it. And we can go and paste it. Bam. Interesting. And here, for this one, Windows Shift and C for color. Take this one. Here we go. Maybe we can put some more colors here and there. So this should go to 0.75. And it should be this one here. So color picker, picking this one. Okay. And here we take dark blue. So we can also, of course, just copy this one here and paste it here. Maybe we should add some more even. Putting the deep blue into there. And maybe, can we put the light blue, the soft blue in there as well? Will that work? No, I don't think so. Ooh, that's hard. That's hard. Maybe we can put this away. I have that. Yeah, that's working, but let's see. Can we add this one here as well? Yeah, that's nice. So now we got to evenly split it. Put this at 0.4. No, that's too hard. Maybe here. 0.2. And 0.1. Do we like it? Is it too much? Maybe 1/3. That's nice. Okay. But it's not yet finished. It's not very nice currently. So what we got to do is we want to have 0 as white in the middle, and that doesn't work with an even number of levels. So we switch to 31. Yeah. And we have white here. But still we have like the mesh right here right now visible indirectly. So we're going to smooth blend it again. And even if we go to higher levels right now, we will still have white in the middle if we have like 511, an uneven number. So that's how I would work with positive and negative. What also does work if you add like splitted color bars like that, adding a yellow here, or maybe even adding a green on the other side of the white. Yeah, that does work. This might also work, but if you have a distinct 0, make it neutral, so make it white. Why not? This could work. This is a preset with white in the middle as well. Here you have black in the middle. That's also an interesting choice, but I wouldn't go for this. So this one is also nice with a small difference in the middle, so you can really see the gradients. Yeah, there are a lot that can work. You could even use something like this with an extra like hotspot, high pressure zone. Yeah, this could also work. Okay, but yeah, or this. If you put several quantities into one visualization, yeah, make sure they don't use overlapping colors. Okay, let's go for cool warm Siemens, I guess. This is one I used earlier, I guess. Cool warm Siemens. Yeah, that's what we're using now. So let's make this one a nice visualization too. Turning off on advanced rendering leads to nothing. Shadows, please. Advanced rendering. Go for matte. Go for clear coat. Yeah, but now that we have white, this might be misleading if you have a white shadow on it. At that point, you really need to think about, okay, I'm focusing on more visual representation, or I'm more focusing on the engineering view. Let's put some orange and yellow in here before we go further. Orange, RGB at 0.8, and some yellow at 0.64, 65. That will look awesome. Yeah, that's good. Okay. And yes. Oh, for plus minus color bars, you should always make sure that you have 3 or an uneven number of labels, so you don't hide the 0. See, that doesn't work, but an odd number does work. I use that one. So, have we more parts in here? If we had time right now, we could take the DrivAer geometry with all the surfaces that we have split up, yeah, like here, like there, and make them different displayers, or we just steal it from the things I have done before. For that, we just need to find the other scenes, which is here. And we just say rims, tires, powertrain, suspension, exhaust, brakes. Yeah, come on. Copy. Ah, there's even more. Let's just details and lights and SimCenter badge. Yeah, come on. We're taking it all and putting it right here, right now. Okay, we don't need the body, obviously. Let's refresh it to have the correct order. Here we go. Here we go. We have something interesting right here. Yeah. I think that does work. I like it. You can even see that the front lights are working. So now we can switch the background again. The background color from solid to environment map. Can I look inside, or what's that? Yes, I can look inside. That's crazy. Yeah, I like it. Let's maybe... which one did I hide? The details front, I guess. Now I want to see them. Even though it's a bit confusing. The windows, we can still look through them. Because it's glass body reversed. So if we go for our tools and our rendering materials and look at our glass body reversed. Let's just say the transmitted color is just black. Nah, it's the wrong one. We need to go for the transmitted color of glass body reversed. It becomes black. Not sure if that's good. Oh, that's nice. Okay, let's keep it like that. Cool. See, these are some single light reflections that might stay a bit noisy. Yeah. They might get blurred out sooner or later by the noise reduction at the end. Okay, let's see if we can do something with the pressure coefficient still. No, I think that's okay. Do we have shadows? We do. That's our finished image, I guess. Pressure coefficient. Nice. What else could we do? We could put a full wind tunnel around, which we have in the other setup, and just so it will look like this at the end. Let's just open the other scene for that. This is what I have done earlier. This is just the Reynolds average Navier-Stokes version of the large eddy simulation that I had done before. And as you can see, it's basically the same, but with less turbulence fidelity. So let's see how this is made up. It's all just dead displayers that show some geometry around. But what is important is right here. There's a displayer called Q criterion, and it is an isosurface. Okay, let's look it up. Isosurfaces can be found under derived parts. Isosurface is here. See, that's our isosurface. It goes to our region. Yeah. Not the display, not the boundaries. And the and for a scalar field, it has Q criterion as a value. Let's look at it like this. And then you typically go for Curie and pick your ISO value that you want to have in your displayer. And then it's more likely drag and drop it over. Ta-da! For the visualization, I then said, okay, I want a matte displayer here with shadows actually. And I manipulated my color bar. So at the darkest color, that's velocity magnitude. The darkest color, I set the opacity to 0. Then I'm slowly ramping up here. That's opacity 1. Ramping down again. Ramping up. Down, up, down, up, down. You can even make this more intense. Something like this. See? Adding another peak here. And making these peaks here sharper. And making here a down peak. And here. and here. Yeah, so you get more separated clouds. That can sometimes work really, really good. Yeah, but don't overdo it like I just did. Okay. The second thing that can be quite interesting is not isosurfaces, but so-called resampled volumes. So let's put this one away and yeah, turn one light on because we can't see. Is it perspective? Yeah, it is. So what's a resampled volume? A resampled volume is it's just a block of geometry, like you can see here. Yeah. That is, go to that view, please. And in this part, the volume is, yeah, Barut's resampled, re-rendered, interpolated. And we can put this into a surface displayer. That was wrong. You don't put it into surface displayers. That's not true. I'm sorry. You put it into scalar displayers. Okay? And then you select whatever you want to see. So for example, vorticity around Z or I in that direction. Yeah? So we're basically now recreating one of these images that we just had. Something comparable to this. Actually, yeah. The eclipse. Exactly. So, yeah, let's take this first. Whatever. We don't see a thing. That's bad. That's really, really bad. So we call this vorticity. Maybe around X. So this color bar doesn't work. We have that positive and negative here again. So we need to have something with a decent zero in the middle. So why don't we just use the cool warm Siemens that we just used? And of course, making it something like this. And of course, this doesn't work. We need to make this even, first of all. So that we have a clear zero in the middle. So let's go for -1000 to +1000. Don't know if that's realistic. Yeah, let's see. I can't see anything. Maybe even less for start. Okay, it's all white. Yeah, that's like nonsense. So why is it all white? Because it's 100% opacity everywhere. So we added a compy and call it color cool warm Siemens transparent. Bam. And first of all, we set the white value to 0. And we can, for the first time in history, we can see something. Ladies and gentlemen, we got them. So let's make some more peaks here and there, and here and there, and here and there. And now we're dragging them around. Let's have one at yellow, one at orange, one here, and one there. And we need another one, I just noticed. Well, maybe not. Let's just have 3. And now we're putting these somewhere here, somewhere there, somewhere here, somewhere there. Oh, So this is 0, and this is 0.5. And here, here, and here. Whoops. And here you go. And here you go. Here you go. So what do we have here right now? Yeah, that's not yet perfect, but we are working on this. So needs to be less opacity, so like something like that. And here we need to put it down. And maybe we can decrease this as well. And I think most is happening in the middle. So let's tune it for that. So let's go for -10 and +10. I'm not sure. Is it really swirls around that? That's still very, very wide, isn't it? It's crazy. I'm wondering if that field function is actually correct. Vorticity around X. I want to have the swirls in that direction and that direction. Should be correct, but never mind. -3 and +3. At least we're... Ooh. Yeah, there's something to be seen, I guess, right now. Yeah, let's go back to -10 and +10. Yeah, as you can see, it requires some modification, obviously. But like that. And now we're mirroring it. Transform. Symmetry. Sorry. Maybe this could do a trick. So let's turn off the lights and I glow. So no, not perfect, but that's something we can start with. I really like how we can see the swirls around the mirror right now, but to be honest, this image is far from perfect from my standpoint right now. Yeah, this needs decent fine-tuning. Yeah. Okay. What else can we talk about? Well, I want to say a few more things about the DrivAer itself, because that's obviously not my model. See, it is something brought up by the TU Munich. So if you Google for DrivAer, you will go to the Munich Technical University, and then you can find the geometry right here, and then you can see smooth or not smooth, yeah, with gearbox, exhaust pipe, engine, stuff like that, yeah, with mirrors, without mirrors, to the download. Okay, right, yeah, thanks for them. These models are typically used if you compare solver A to B, yeah, and that's where we came up with that simulation in such a competition. Yes. Okay. I think I'm done for today. That was a quick walkthrough. I guess I have to thank you very much. If you have further questions, it is now your time to chat. Yeah, I can still answer them. And if there are no more questions, I would just say, okay, thank you for your attention. And we will tune in next week to finish the other secret project that I'm still working on, which is something more civil engineering. And then we will continue with that simulation so I can get it out of the door. If you are really interested in these simulations and maybe you want to explore them in virtual reality, I have free tickets for Hannover Fair to spend. Yeah, just visit my LinkedIn profile. Yeah, this one right here. And you can find in my latest posts, you can find some more links, and there is free tickets for Hannover Fair, and I will be there as well. And we can meet there, and you can explore some interesting simulations in virtual reality, actually, because you can also enter these scenes with VR goggles on. Yeah, and maybe we meet there. Maybe we just meet online next time. So make sure that you tune in. Next week, the week after, I won't be here. But this content will also make it to YouTube in the next week, probably. And yeah, thank you for tuning in. Have a nice day.